Hello, Physics 135 students, and welcome back for the final virtual class of the semester. Today, we're going to be discussing a few really fun topics, although it'll be a shorter lecture. Before we get into that, your final exam is not posted quite yet, but should be posted quite soon. It will be due on Wednesday, May 6th, and it's not an upcoming deadline exactly, but please make sure to get in your late assignments for me to grade as soon as you can, ideally by this final exam date. Final grades are due Monday, May 11th, and I typically try to get them submitted within a day or two of the final exam. So please email me if you need any help identifying what to prioritize, or if you need me to check on your grade or anything like that. I'm happy to be of assistance. And then for today, we're going to be looking at a couple of different kind of open-ended topics. We're going to start with inflation and string theory or superstrings. We're going to really then have more of a worksheet on grand unified theories and theories of everything. And then there will be a short lecture on the fate of the universe. Overall, most of the expected class session time today will be on the worksheets. Although even with the worksheets, I think that this would be a little bit of a shorter lecture because it's meant to be quite open-ended. So it depends on what really you want to dig into more as part of the worksheets or beyond. So first, for inflation, we have a pair of goals for learning, which constitute your first two attention checks. First, what are three mysteries that are relatively unexplained by the Big Bang Theory, and how does inflation solve those mysteries? Second, how is the geometry of the universe affected by the critical density? And we'll get to defining what the critical density is as well. So first, regarding those mysteries needing explanation, there are three big puzzles. There are actually maybe a few more big puzzles of the Big Bang Theory, but the ones that we'll be talking about today are related to where structure comes from, why the overall distribution of matter is so uniform. These are, um, in many ways, kind of like the same mystery, but nevertheless slightly distinct. And then third, and really separate, why is the density of the universe so close to the critical density? All right, so we've talked before. In fact, last lecture we talked quite a bit about the CMB and the power spectrum and temperature variations, which is intimately related to these first two. So you might be wondering, well, why do we need inflation at all? Like, glossed over things a little bit that lecture since inflation is more of an extended topic rather than a core concept. And the key item here is that these temperature variations really should not exist if the universe was in thermal contact during its history. When two objects are in thermal contact, the first law of thermodynamics says that heat will move from the hot object to the cold object, or in other words, you'll reach an equilibrium at constant temperature. If there was some equilibrium established at constant temperature, then we wouldn't ever end up with this picture. And in terms of talking about the Sachs-Wolf effect or the idea of baryon acoustic oscillations, in other words, another way to put this is, well, why was it that there were slight overdensities and slight underdensities in the initial universe, given that if the universe was small enough early on in its history, then there should have been thermal contact. So when was it that the universe got so large that even light could not propagate those effects through radiation pressure? And the idea here for inflation solving this puzzle is that inflation basically there is expected to have been tiny quantum fluctuations. And then again, if enough time elapsed, those would have been in thermal contact. Instead, the idea is that there was a rapid exponential increase in the size of space in this event, so-called inflation. And then if those quantum fluctuations were blown up to really, really large sizes, like astronomical or cosmological sizes, then due to their extent, there simply wasn't enough time for light to travel from one patch to another before the CMB got emitted. And therefore, inflation helps to explain why there were structures that arose in the early universe. So, another way to kind of better understand this is looking backwards in time. So here we are at the top in this diagram. And then if we look back at two gas clouds that are separated by a certain distance, um, we can see things that are related, are at a distance to us related to the amount of time that's elapsed, since the speed of light is 1 light year per year. And we cannot observe anything outside of this so-called light cone. Now, imagine for inflation that there was a period of exponential expansion. In that case, space expanded faster than light could communicate signals from one patch of space to another. And that would allow for these two very, very distant clouds, which otherwise in their past history would not have had a chance to communicate. They would have been able to communicate very, very early on and before they got separated. So that helps to explain not only why there is structure at all, but why the CMB is so uniform. Otherwise, it could be that the universe just started out really, really big, which would explain why there are temperature variations. It doesn't explain why the temperature variations are relatively small on the order of 10 to the minus 5. And inflation, at least supposedly, helps explain that. All right, now related to the mysteries that of the Big Bang that we're getting through why inflation answers them, to understand one of those mysteries, we have to understand what this phrase means of the critical density. And for Einstein's theory of general relativity, we can come up with certain solutions. And the solution that describes really the evolution of the universe as a whole is called the Friedmann equations. And so this h is the Hubble parameter, about 70 kilometers per second per megaparsec, which is related to the expansion rate of the radius of the universe divided by the radius of the universe. So this Hubble parameter, this evolution in terms of the expansion rate divided by the current size squared, this is related to the overall mass density. This includes not just regular gas that we can see, but also dark matter. And it also, as well as radiation, I should say. It depends on this K, which is the curvature of the universe. And then it depends on dark energy as well. And since dark energy we think is a constant, G, pi, 8, 3, etc. are constants, for a given size of the universe, the curvature has a specific value depending on the density. And in particular, the there if the curvature is 0, that implies a very specific value of the density, which is what we call the critical density. Now, in terms of the geometry of the universe, if the density is critical, then we have again that the curvature is 0. So that means that we have a flat universe if there is 0 curvature. If the density is greater than the critical value, then that leads to a positive curvature, which implies that we have a closed universe like a sphere. On the other hand, if the density is less than the critical, then the curvature ends up negative. We end up with a saddle-shaped universe, like if you imagine a horse's back being here. And so these are three different geometries for the universe. And then by measuring the CMB, we end up with something that looks extraordinarily flat, which was very counterintuitive. People thought initially that the universe was most likely spherical, but maybe this weird saddle shape. But the fact that the universe is flat suggests that the universe has to be really large or potentially infinite, in its shape, and that was counterintuitive for people that thought that the universe was expanding but might eventually collapse back down to a point again. And so, in terms of understanding the curvature of the universe being flat or effectively flat, I might say, if the let's say that we nevertheless do live in some sort of spherically shaped universe, right? We initially started out with a point and then expand that balloon larger, larger, larger. It's always positively curved, but at some point you don't notice that it's curved anymore. And so that's still kind of my preferred view of the universe's geometry is that we're flat within measurement error and presumably positively curved, although potentially still negatively curved when, to maybe 8 decimal places or once we get to high enough precision, which we're not quite at, although we do know that whatever curvature there is must be very, very small. In other words, the universe has to be really, really big. And so then that's kind of a puzzle that inflation helps to solve. Now, in terms of how light behaves in these different universes, if the universe is closed, so again in that sphere, the idea is that if you have initially parallel photons, they'll end up meeting, just like if you and someone in the southern hemisphere decide to kind of take random trajectories along the Earth, then there will be a point of intersection. Now, you two might not run into each other depending on where you started, but there is nevertheless intersection points for a closed universe for any two curves. For a flat universe, you can have absolutely parallel lines, and for an open universe, most parallel lines will end up diverging. So it's not just that they stay parallel, but they get infinitely far away from each other with time. In terms of the critical density, we often represent that the density divided by the critical density as a parameter called omega naught. So in terms of the geometry, for these triangles, we actually have the same length for the triangle for the bottom part here in all three cases, but notice how the angle changes. So we have, if this is an isosceles triangle, then each angle is 60 degrees. For the sphere, we end up with something typically where the all three sides add up to much greater than 80 degrees, or at least they can. And for the saddle, we end up with a opposite situation. It's a little bit less evident, but we can end up with angles of less than 180 degrees. So in other words, if we measure the CMB and specifically do this triangle measuring, we can determine what the shape of the universe is, really independent of that consideration of the critical density before. And what we found is that the hot and cold spots in the universe really do seem to match a flat universe where there is not any extra bending of the light towards or away from us. And instead, we end up with so-called triangles on the CMB sky that add up to 180 degrees, or where their angles add up to 180 degrees. And in terms of the CMB power spectrum, you seem to agree with the predictions that have been made by physicists that have studied inflation. Okay, and so now we have a lecture pause. You all will be filling out an inflation worksheet to help you better understand this material. So please pause the video and work on that material now. Okay, so unpause. Next, we're going to talk about string theory. And within string theory, the idea is that everything is ultimately a set of one-dimensional strings. In contrast, in the standard model of particle physics, where we have electrons and photons, etc., the idea is that everything is ultimately a zero-dimensional point. And then we have issues. If you think about two electrons, what would happen if those two electrons end up overlapping? Because the Coulomb force depends on the inverse of the distance, if we have r equals 0, then we're dividing by 0, we end up with an infinity. So that is bad or badness. Whereas for a one-dimensional string or one-dimensional entity, that does away with this zero-dimensional point issue. Now, in string theory, the idea is that these one-dimensional strings are either closed loops, is what I typically imagine, or the other option is that they could be open strands. And as far as why, if everything is a string, we still end up with things that appear very, very different, like electrons or protons, the idea is that the mass and charge depend on the vibrational modes. And in some ways, this is a very beautiful picture. It goes back to um, Pythagoras' idea that the universe is music, or the harmony of the spheres, not only by Pythagoras but also Kepler. And so there's certain really symmetric or beautiful elements of string theory. Other benefits is that string theory naturally includes gravity in addition to the other forces, forming what's called a theory of everything. And the predicted energy scale for string theory is 10 to the 19 giga electron volts. In other words, a very, very high energy that just so happens to be the same as is predicted for grand unification. So grand unification is not including gravity, but combining electroweak and strong forces. On the other hand, there are serious concerns with string theory. One is that string theory predicts 10 to the 500 possible universes. And this arises the question, is string theory really science or just pure abstract mathematics? Because it is unclear which of these 10 to the 500 universes we live in, and therefore it seems like in some ways string theory is not falsifiable, because if we make a measurement, that doesn't necessarily mean that string theory is wrong, simply that we are not in one of those 10 to the 500 universes that we might have been considering. Now, the other concern about string theory is kind of counter to our at least naive expectations. It would seem that there must be higher dimensions compared to the three spatial and one dimension of time that we otherwise notice. In the original theory of string theory, it required 26 dimensions to be a fully consistent set of instructions that produced some sort of predictions. A little bit later came along so-called superstring theory, which, due to certain symmetries, reduced the total number of dimensions from 26 down to 10 and used those symmetries to link matter and forces together. And then M theory found some additional symmetries between 5 different superstring theories and unified them into a single, still string theory, which is referred to as M theory. So, and no matter which form of string theory we're considering, there are a lot more dimensions than we otherwise observe. It's possible that these dimensions are very, very small. I'll let you all puzzle that a little bit more in the worksheet. Speaking of which, go ahead and now pause the video and work on the so-called superstrings worksheet. Okay, unpause. So you might have noticed that although it's called superstrings, it could just as well be called string or M theory worksheet. I kind of like the name superstrings best myself. Okay, and now intimately related to superstrings is this idea of unification. So please work on the unifying theories worksheet next. And this really includes quite a bit of, not a ton, but some write-up, which is useful for you addressing the prompts. So I hope that you all enjoy it. It goes a bit into the history of science, and Simon Singh discusses a few things similarly in what was our main course textbook before we switched to the OpenStax readings. All right, and now for the final part of lecture and for the final part of this class altogether. And so please pause the video and work on the unifying theories worksheet. Okay, unpause. Now we should move on to the fate of the universe. And we will be addressing these two goals for learning, which are two attention checks. First, what are the three possible fates of the universe? And relatedly, what is the underlying assumption that means that there are only three fates that are possible? And last, how does the critical density influence the fate of the universe? Or really, this could be expressed as what sort of balance is required. Okay, so in terms of the fate of the universe, the overall motion, we could say, of the universe or its dynamics depends on only two things really: the initial expansion rate and the net acceleration. So this is just really introductory physics concepts here. Now, in terms of the net acceleration, that is a balance between gravity on the one hand and dark energy. So gravity is trying to pull the universe back together. Dark energy is acting to separate everything in the universe, or it's a anti-gravitational force is another way to put it. Now, in terms of this picture, this very simple, kinematic picture, just like throwing a ball on the Earth, there are only three possible options. First, the kinetic energy can be less than the potential energy. In that case, the ball will, go up after we throw it, but then it will come back down. And for the universe, the kinetic energy is related to its initial expansion rate. The potential energy is related to, well, the critical density or the amount of material that is pulling it, back together due to gravity. And this picture, just like for the ball, the universe kind of goes up in terms of its size, and then it goes back down in terms of its size until it collapses back to a singular point. And for this case, um, we will have kinetic energy less than potential energy. If the density were to dominate over dark energy, in this case, you'd really need a vastly exceeding the critical value for the critical density. Second, we could have the kinetic energy perfectly balanced potential energy. Now, this would have to be, a perfectly balanced operation. It's not expected. In this case, a ball would escape the Earth, but it would, slow down, slow down, slow down as it's, um, you know, balancing its kinetic energy and potential energy. And for the universe as a whole, the universe would expand and then end up coasting. It's a little bit different, right? Because whereas for a ball on the Earth is not changing its mass, and therefore the potential energy required to leave the surface does not change. As the universe expands, all the matter inside of it is getting farther apart. In that case, because the gravitational force is an inverse square law, it means that the gravitational force weakens the further the universe expands. So if the universe is expanding at just the right rate, kind of balancing the net acceleration, then we end up with a coasting solution, so a constant speed solution compared to this asymptotic solution for the Earth. And then in the third case, we could have that the kinetic energy is greater than the potential energy. And this happens for rockets that we launch from the Earth, or in this ball analogy, then the ball would escape Earth and get to just some finite speed. Again, the ball with the Earth is a bit different than the universe. Again, as the universe expands, the gravitational glue becomes weaker and weaker. And that means that as the universe expands really at an increasing rate, eventually the speed at which the universe is expanding will exceed the speed of light, since there's nothing that can possibly stop this acceleration process, we think. And at that point, all structures would stop. This is the so-called Big Rip, where just everything kind of disintegrates, if you will. Now, in terms of the underlying assumption, this assumes that dark energy is constant, whereas if dark energy is also changing, then that significantly complicates the picture. It's still initial expansion versus net acceleration, but just like how gravity changes with the size of the universe, it's possible that dark energy also changes with the size of the universe. Okay, and let's say that the universe does not end in a big rip, whereas there is dark energy, so we're not going to be in that closed universe case either. In that case, the universe should keep on expanding potentially forever. And in terms of what the universe would look like, the idea is that everything will have to eventually end up in a black hole, but eventually these black holes themselves will evaporate. So, in terms of thinking out 1 billion years from now, we expect that there will no longer be star formation, not 1 billion years from now, 1 trillion years from now. There will no longer be star formation in galaxies. We'll have totally run out of fuel. All the stars will be dead, just white dwarfs or neutron stars or black holes, as you would learn about more in Stars and Galaxies, which I'll be teaching next semester, at least putatively. And then in 1 billion years, the idea is that all the matter is in these compact objects, white dwarfs, neutron stars, black holes, and then some hot gas. In 10 to the 20 years, the idea is that galaxies will really kind of disintegrate because these compact objects will collide with each other. The supermassive black holes will, basically continue to grow as they collect more and more of this material, and we'll end up with very few objects in the universe, just kind of the central parts of galaxies that'll eventually also merge with each other. In 10 to the 33 years, the idea is that, and this number could become a bit larger, admittedly, as we continue to run more and more particle detector experiments. So we haven't found evidence for proton decay yet, but the standard model assumes that protons have some sort of half-life that must be really, really long. And eventually, protons will decay and we'll run out of those. About 10 to the 40 years from now, the idea is that there won't be any more atoms because all the protons will have finished decaying. We'll only have radiation and subatomic particles. So, in other words, like electrons, radiation constitutes the photons. We might have some neutrinos and some supermassive black holes. And then after 10 to the 100 years from now, all these black holes will be evaporated and we'll just have radiation and subatomic particles, or really probably radiation and neutrinos effectively at that point. Okay, and so in terms of like basically why it is that these black holes will evaporate, the idea is that there are kind of three different ways that material can interact with black holes. One, you can have something that falls onto the event horizon, never comes out. Second, you can have something in otherwise empty space form, and you can have a certain situation where both these particles will just annihilate. If they're close enough, though, to the event horizon, then one particle could leave the influence of the black hole, and the other object could be gravitationally, accelerated, flung into the event horizon. And since this comes at the expense of the space that's just outside the black hole, which is, uh, in other words, the curvature that is caused by the black hole, that means that the black hole is losing energy. It's losing its gravitational energy from that warping of space-time, and therefore eventually black holes, we think, evaporate by this process. Okay, so that is the end of lecture and therefore the end of this course. Again, I hope that you really had a great time. There are 3 worksheets that you all have hopefully completed by now. If you have any questions, whether it's from one of these worksheets or one of the past worksheets, do feel free to reach out, and definitely reach out if you have any questions about the grades. You're almost done, so let's race across the finish line and end on a high note. Hope that you all have a great rest of your week, and bye bye.